Hello, we are the team called Mex, and we are going to introduce you to our mini challenge. In order to carry out successfully the project, we decided to use the project management methodology, known as waterfall, which has been previously employed in other mini challenges. Additionally, the team divided into groups, with two members handling part one of the project and the other two taking care of part two. This challenge is focused on implementing the knowledge we acquire during the class session, specifically by performing an open loop control to enable the robot to carry out two activities, a square and a trajectory chosen by the user. In both activities, we conducted simulation and real life testing. Below, you can observe the development of the two activities.
In this activity, we created a speed control with the purpose of generating a square trajectory for the rock. To achieve this, we created a control node in the non-hollow kinematic sim.py script in which we set the following condition. If the robot has not reached the desired position, 2 meters, we apply a control through the command bell.linear in x. We use a constant called k, the error, and a noise constant to calculate and send the speed to the robot. Regarding the odometry, we created a node called localization v1.py with the goal of obtaining an accurate position estimate. We use the generated movement to perform the corresponding transformation.
Additionally, we create another node called joint_pov, to which the odometry node sends information about the state of the joints in the simulation. This node uses the URLF file to provide an appropriate representation in RBs. Finally, we create a launch file that integrates the three nodes mentioned above. This allows us to successfully execute the activity using the route launch command in the terminal, enabling us to visualize the square trajectory in RBs.
As a result, it's important to note that we observed significant difference between the simulation and a practical execution. This discrepancy may be due to various factors, with the main one being the variation in the degrees the robot used to turn and maintain the square trajectory. In the simulation, the robot follows the trajectory correctly, whereas in practice, the execution is lagged, resulting in deviation from the 19 angle in the inability to complete the square correctly. After conducting investigations, we concluded that is due to friction and the characteristics of the robot's wheels.
The main difference between this activity and the previous one is that you have to request a path to save the points that are given to you to create the trajectory. The major issue we faced when performing this activity was calculating the trajectory angle at the second and subsequent points. In the first point, the angle is determined by the direction in which we place the robot. However, in the subsequent points, we cannot control the angle, as the robot can turn in any direction, potentially disrupting the angle calculation.
The program we developed asks the user to provide the x and y coordinate points along with the time at which they want the robot to reach each point. All the information it receives is then passed directly to the nodes, but now as a custom message. This is because it compresses the x, y velocity and the desired arrival time into a custom message. In the path generator node, upon receiving this information, there is a node that runs the path, triggering the robot's actions. Similar to the previous activity, that is visualized using an odometry node in RBs.
We perform a trajectory of 4 points, in which, instead of making a square, it deliberately turned to demonstrate the point, as seen in the following video. This activity was the most challenging to carry out because we did not have the necessary time, and there were only two robots working, in contrast to the simulation, where we followed a different path. We perform a trajectory of 4 points, in which we can conclude that there is a wide range of difference between simulation and real-world implementation. This is because there are various variations that can lead the robot to follow patterns other than those specific in the code. This is more pronounced in the issues that robots may face with their hardware, such as their wheels or other components. Despite the above, this activity was enriching in terms of learning more about ROS and how to implement it into motion in our final challenge.